Hey guys, so today we will be proving the addition theorem, which states that the sum of the probability of two disjoint events is the same as the sum of the union and the intersection of those same disjoint events. So to prove this, we're going to have a general proof strategy of splitting into disjoint events and um, seeing under which unions and intersections these disjoint events kind of recombine to get our desired addition property. So disjoint partitions over intersections of unions. So first, I'll call this step. First, we're going to want to partition A. So we can say that A is the same as A intersect B union with A intersecting B complement. And since these are disjoint sets, when we take the probability of A, we have that it's the probability of A intersect B plus the probability of A intersect B complement. And we will call this equation 1. Similarly, we will want to partition B. Partition B. And in this, we will have that B is the same as the events of B that are in A, union with the events of B that are not in A. And then since this is disjoint sets, the probability of B we will have is just the same as before, where we can add the probability of disjoint sets. And we will call this equation 2. Next, let's look at the union of A and B. So if we take A and B, we see that it is the union of our A event here with our B event here. So we can just union all four of these terms and get what we have. So A is A intersect B union A intersect B complement, and then we're unioning over B2, which is A intersect B union of A complement intersect B. And the union of the same two events is just that event, so we don't really have to count A union B twice. So our three partitions that we get for A union B is A intersect B complement union A intersect B union A complement intersect B. And moving this into the probability space, we have the probability of A union B equals the sum of the probability of the events in the disjoint sets, whether they occur or not. So the probability of A intersect B complement plus the probability of A union B plus the probability of A intersect B. And so now we can actually call this equation equation 3. So we have the probability of A, the probability of B, and the probability of A union B. Now, going back to what we were trying to prove, let's see what is P of A plus P of B. So P of A plus P of B is this plus this. So 1 plus 2. And so that equals probability of A intersect B plus probability of A intersect B complement plus the probability of A intersect B again, but this is from the B part, plus the probability of A complement intersect B. So simplifying this, we have two, or we have the probability of A intersect B complement plus 2 times the probability of A intersect B plus the probability of A complement intersect B. And if we compare this equation with this equation, we can kind of notice that the only things that we have missing from this to make it equal to this is that we're missing a second probability of A intersect B. We only have 1 here and we have 2 here. And so from 3, we can add probability of A intersect B to both sides. So therefore, we have that the probability of A union B, and then we're adding A intersect B to both sides. So A intersect B is the same as the probability of A intersect B complement plus 2 times the probability of A intersect B plus the probability of A complement intersect B. And what we can now notice is from our sum here, this is the same as this, so therefore the probability of A plus the probability of B is the same as here. It's the same as the probability of A union B plus the probability of A intersect B. And so this is the addition theorem that we just proved using disjoint sets for A and B. And this is this kind of same as there's some Venn diagram A, there's some Venn diagram B, and then there's some probability measure space, and everything here and here is A complement, and then this middle section is A intersect B, but then this whole section is A union B. And so what we're kind of trying to do is not double count the middle. And if A and B are disjoint sets, we don't end up counting the middle and we prove the addition theorem. Thank you.